So it's nice to come to SAAO. I came here a few years ago to give a general cosmology talk. And today I'm more delved into the content in the universe, which is about cosmic baryons. And first of all, I'm from Stellenbosch University, 40 kilometers east of Cape Town. So I welcome the international guests to visit there if you have a chance. It's a very beautiful town and very relaxed to be there. Do we have a pointer? You see, this is a third world country. You don't have a pointer? Right. So I think everyone knows this pie chart, the numbers, dark matter, dark energy. But where these numbers come from? Well, the number come from the fitting of the cosmic microwave background anisotropy, the anisotropy power spectrum in the C and B. I mean, this is the Planck full sky map, and that's the angular power spectrum that measure from this. And by fitting the 6 cosmological parameters, you can constrain omega b h squared, and that is the number you get. Right? And the number of the baryons can also come from that 4.6%, can also come from the primordial deuterium abundance. So this is the measurement from the quasar. So you have a distant quasar, and that emits a continuous spectrum. And as the quasar light propagating through the intergalactic medium to you, it will go through all of the cold intergalactic medium, and where you will see the whole spectrum redshifted towards higher wavelengths, and then you see a lot of absorption trough. And that's where it comes from. So here you see a lot of absorption trough, and wait a moment. Then you will be able to measure the deuterium one and measure the primordial deuterium abundance from this very metal core system. And here we go. I mean, from the very prominent Lime alpha peak, you can determine the redshift of the distant quasar, and then from there you deduce the rest of the abundance, and this is what we get. So that's the deuterium abundance, the middle panel. Do you have a stick or something? Stick. And then what you measure is a y-axis on that plot, and then the line is actually the standard Big Bang nuclear synthesis calculation, and the band, you see there's a certain thickness of the band, and that band is the band indicating uncertainty of the cosmological parameters. And basically, you measure the y-axis and find the value of the line, and then reverse back, you will get a baryon fraction. And why is that? Because more baryon there is, then there will be an active nuclear reaction going on at the early universe. More proton and neutron will be converted into helium and so on. Therefore, higher baryon abundance will result in a more higher helium abundance and less deuterium, which is a midway between the primordial synthesis to the helium, right? So therefore, from that relation, you can get a baryon abundance. And then we are really in the third world country, maybe even maybe in the Hong Kong society. Welcome to Africa. From here, you're able to basically measure omega pH, right? So then you got that number. And the third way of measuring that from the fast radio burst. So people have been measured a lot of localized FRB, and this is a famous paper by McQuaid et al. 2010. And then they measure 6 localized FRB, and by measuring the dispersion measurement DM, they can convert that dispersion into the baryon density, and that is the number they get, 2020 in Nature, and there is some recent update on that with a smaller error bar and so on. Now, if I put together these 3 numbers together, the one which I mentioned, the DLA system, the Lime alpha system, up, Planck cosmic microwave background radiation, left, lower left, and also the DM from the fast universe, you got the same number. 3 different, completely different measurements. You got the almost the same number. isn't that impressive. So it's just like knowing what happened in the first 3 minutes of the universe, which is hot Big Bang, is already indicating the plasma, the baryon behavior 380,000 years after Big Bang, and already indicating billions of years of the intergalactic medium of the loss of structure, isn't it? So I feel that if this doesn't impress, this means the model really works. I feel that if this doesn't impress you, you probably have no soul. My take of this famous problem is baryons are never missing. That's a very confusing term. We just haven't counted enough of them at low redshift. So that's my statement. And what is the problem statement? Where the issue come from? I mean, this is the cosmic baryon inventory that this paper, Peebles 2024, has counted all of the baryons that made into stars and galaxies from all of these components. So if you add them together, I wouldn't read out. If you add them together, you got this small number, 0.0035. And that number divided by the previous number, 4.6%, is about 10%. Is about 10%. So basically, only 8 to 10% of the baryon density made into stars and galaxies shining to you, but the others are not shining to you. And that's the story. So if I look at this diagram again, I would have a better understanding of this diagram. So dark energy is this big amount. The nature is not known. Is a number in Einstein field equation. People fix that number, etc. We joke about Robert Caldwell, Dartmouth's colleague, inventing crazy model for the dark energy, and also intrinsic model. Yeah, and also dark matter is something gravity. It's gravitate but nothing else. It helps to form the galaxy like our own, but nothing else. We don't know the particle nature of dark matter whatsoever, right? So that's something we know. And that pie chart, the smallest one, 4.6%, I would draw another line in that 4.6%, which is 90% is we know is there because that 3 measurement has already gave you the number, but we don't know the location. 10% of the 4.6% is that you know their atoms and they are shining to you, and we know their locations, the center of the galaxy of the stars. So if I put another little line on this chart, a little partition, I will put that line over there to indicating what we really know of. Of course, searching for dark energy is an ambitious game, but today I'm looking at a little bit more accessible, tangible thing is to search for where at that 90% of the 4.6% is. So there's early simulation by this Sen, Renyue Sen, and Ostriker Princeton team, 2006, to show actually there's a lot of diffuse component of that 90% of the baryons that in the intergalactic medium that basically prevail around filament and even voids. So they calculate the mass fraction in their computer simulation as from redshift, and you can see at low redshift 1 to 0, you see a lot of them are in the status of the warm hot intergalactic medium, WHIM, this red thing, with temperature 10 to the 5 to 10 to the 7 Kelvin. Of course, they are not super hot, 10 to the 8 level, not that high level to shining in X-ray emissions and so on, but nor too cold already that made into stars and galaxies and etc. You know that they are kind of in this lukewarm situation, this kind of medium temperature. And then later on, there's an illustrative simulation further shows the relation between baryon density and dark matter density. And this graph is interesting because this shows how does the baryon distribute according to the dark matter density. And this line shown over here has the mean value of the slope baryon density omega b divided by omega n, the cosmic mean value. So if everything is, if baryon is completely tracing the underlying dark matter, then supposedly all of the points reading from simulation, all of the color dots should be following exactly on this line. But you see something different. Here is the halos, which has an occupied higher density. Here is the filament. I measure use my mouse because the people on Zoom wouldn't be able to see it. So here is the halos, but it doesn't show in here on this. Okay, so I can only take one. All right, so maybe I just, sorry guys online. So here is the halos. You see that halos offering a higher density, filament in the middle and void. Look like there is some removal of the baryon over here to enrich void and filament. I'm taking some dots over here to enrich that part, isn't it? So that's the whole story. You have to quantify the total baryons in the H1 ionized and the baryons, and also the baryon in filament void. So to complete this equation, to find out whether these three things, everything added together is 100%, they must be there. They must be 4.6% in total energy budget. But then, can you confirm this? Of course, people can always confirm this from simulations, but we need observations. We need more kind of a straightforward evidence. So my LSST proposal 2021, when I submitted to the LSST council, is to doing different projects of halo, filament, and void to check up that equation observation. So that is my proposal in 2021. And now it's 2021 though. We started in 2022, right? Or 2023. Now it's probably a 2 year or 2 or 3 years past. I can tell you this check mark. The number C is still ongoing. This is not yet, but the others check mark. So today I'm going to show you this check mark. That's it. First of all, before we start, I will frequently use this effect called Sunyaev-Zeldovich effect. Who are these people? And these are two ex-Soviet Union scientists, Rashid Sunyaev on the right and Jacob Zeldovich on the left, who have pioneered this study of the Sunyaev and Zeldovich effect. Right? And they wrote this early paper in 1970s or 80s indicating this effect. But by then, there was no observations. They were hesitated to write it down because they think it's too small to be observed. But one day, it is really being observed. So even though you find some, that gives us a lesson that if you find some small effect, don't hesitate to publish a paper. Because decades later, people will measure that and they will respect you as a pioneer. So that's a good message. So first thing is about thermal SZ effect correlating with weak lensing. And why we do that is because weak lensing is better measurement of the tracer of the underlying dark energy distribution. And SZ effect is what hot gas is sensitive to. So we are basically correlating that two and extracting the hot gas information. So today, I'm not interested in the primary CMB. I'm not interested in the temperature and absorption on the cosmic microwave background radiation that formed 4,100 years after the Big Bang. No, because those ones are characterized the initial condition of the universe, which is I'm not interested in today, although that's interesting in general, but not today. But today, I'm interested in this effect. As I said, the thermal Sunyaev-Zeldovich effect. The effect is simple. The microwave background radiation serves as a backlight propagating a long way from the last static surface to the observer. And it will go through a lot of intergalactic medium, a lot of hot gas, etc. And those hot gas will inverse Compton scatter the background CMB photon and produce a secondary anisotropy distortion in the CMB photon. So this is the effect. The primary CMB, which is really formed, at the last static surface at the decoupling epoch, is a black body radiation. You know that story from Kobe, right? The famous Kobe plot showing you the beautiful black body spectrum. And but after this distortion, because the hot electron transfers some energy into the photon, it will shift the whole spectrum a little bit to the right, because the higher is frequency on the right. So therefore, you will see a decrement on the lower frequency part because it shifted on the to the right. Here you receive a decrement, and here you receive an increment. Right? And then if you can measure that distortion effect, then you can separate this out and to measure this Compton Y parameter from here. So you can measure different frequency band and eventually come up with this Compton Y parameter. So here is the delta over T when you measure from the CMB, and that equals to a frequency dependent factor times this Y. And then you can measure that. And then by knowing G mu, you can deduce what is Y, the Compton Y parameter. And that is the integration of the pressure, K, T, G, and N, the electric density, the pressure. That's the integration of the pressure along the lines. So then you can measure the pressure profile of the hot gas and so on. So this is why only after WMAP, only at the Planck era, the European satellite Planck era, that we can do this. So the upper panel is the WMAP satellite. You can see the 5 bands all here on the lower frequency side. But for Planck, it has a distribution of bands, frequency band across all different frequencies. So it's something more possible with Planck. There we go. This is one of the early maps that we produced by using the published Planck data. And this is the early lensing map we used for the CFHT, the Canada, France, Hawaii lensing map. And this is in total 154 square degree in 4 patches. But this is going up very rapidly, which I will explain to you in a moment. And now I'm correlating the two. So this map looks very noisy. I mean, apart from the galactic plane, which obviously, but on a higher latitude, it's very noisy. But there's a signal. There is. And once you correlate the two, correlate this one with this one, here is a signal. Here is a signal that is consistent. The black dot is consistent at about 5 to 6 confidence level across all different temperatures between SZ and lensing. And then I did we did a fitting for that data, which is the halo model. And then you can see if you allow the hot gas to, I mean, the halo model need to allow the gas to extend to a radius of the 5 times of the radii of the central halo. Then you will get a curve, which is the purple line, matching the data. If you only allow the hot gas to be in the center of the halo, then the curve is lower, which is the red line over here. That is being excluded by more than 4 sigma confidence level. So that means the hot gas is much more extended than the central halo and towards a larger radii and 5 radii, etc., that are no longer to be associated with the central halo and is more sort of diffuse than the center of the galaxies. And in recent years, we have there is another study on this from the Atacama Cosmology Telescope ACT, and they stack the KS effect. And so from their data in 2020, you can see that the signal is over here, that is way above the NFW profile. And also a lot of data indicating the hot gas is beyond the Virgo radius, this is Virgo radius, beyond the Virgo radius of the central galaxies. So that is a better result than us because it's a few years later by using ACT and higher signal noise ratio. But the one which we did is kind of the first evidence of that. And you can also kind of separate that signal into different redshift and mass, and you find eventually the equivalent temperature is about 10 to the 5 to 10 to the 7 Kelvin. That is exactly matching the simulation that previously did by Sen and Ostreicher's team in 2006. But this is more from comparing the model with the data. From that, we can deduce this. So here I fast forward to a recent progress by using the estimator that I provided early on. So the first one is our own update of using RCS lensing. You see the sky coverage is larger than that, 536 square degrees, and eventually we get about 8.4 signal detection. And here is a KISS survey, the European Southern Observatory KISS, also a photometric data correlated with Planck and ACT. They got 9 sigma, and darkening survey, year 3 lensing will get 21 sigma. And at the moment, I mean, this is the check mark which I showed previously. At the moment, we're doing the decals lensing data correlating with ACT combined data, and the signal noise will be a lot, will be about 40 sigma. So just for 10 years, we move from 6 sigma to almost about 40 sigma for these measurements. And this will really be able to pin down the baryon distribution and so on, and also even constrain some of the feedback model that can popping these baryons away from the center of the halos. Yeah, and all of this are before LSST. All of these are using photometric data. So we are preparing for the LSST, which produce billions of galaxies with photometric data. It will be a huge signal noise ratio. Okay, so then we see this general correlation between the two mass tracers. And the second study we did is to see the eviction of those baryons from the halos. You remember that first plot. There is an eviction of that baryons and to enrich the void and filament. I will show you the eviction first and to show you the enrichment of the filament and void so that you will believe what I show you, the check mark, all of this. All right. So if I want to show you the eviction of that, I must show you what is the deficit of the baryon in the halos, right? So and we can do a stacking. Now we have a lot of data. Now we can do a stacking to show you and to fit profile and to show you where that deficit is. So this is the universal pressure profile provided by Anwar et al. Right? Initially, they only fit the profile with very low redshift below 1, and very massive central galaxies. But we do it something different. We do it, we include a much larger sample in mass and redshift. We include the DR4 counter Y map, and we also test off-sampling problem. Here is the data. So we allow a much wider range of the mass distribution, and also we allow a much wider range of the redshift distribution. Previously, as I said, they only below redshift 1, and now we extend all the way up to 1. For LSST, it will be all the way up to 2 and maybe even higher. So certainly that will be confront a much more stringent study. But at the moment, our sample go to redshift 1, right? And then we do a stacking. Here we go. Well, then we do a stacking on active map. And you see, here is redshift distribution from low to high. And for different mass spin, this is the lowest mass spin, this is the highest mass spin. For each spin, you get a very decent detection, more than 3 sigma. Even for the high redshift and lowest mass spin. This one is supposed to be weakest, but still a very clear detection. And of course, if you add all data together, the detection is very significant. I forgot the number here. I should write it on the. If you add them together, it's more than 10 sigma, but each of the panel is more than 3 sigma. And then you can fit a model. You can fit that proposed universal pressure profile model to that. But then you see, and you can certainly get constrained to get numbers of this, and that's a total 100. It's probably too small to see, but I want to illustrate the most important part, which is this parameter people are interested in. This one, BH. That is the hydrostatic bias. That is where you put that bias in front of the halo mass and calculate your gas mass that are sensitive to your pressure profile. So if we basically fit that parameter BH. You see across all different mass spin, these are different mass spin and also different redshift spin, like indicating different colors, they're all about 30%. All about 30%. That means roughly 30% of the mass is being removed to enrich the others. The real mass that are sensitive to your pressure profile is about 70% of the halo that is gravitationally interesting. So this is evidence to show that there is some eviction of the deficit of mass responsible for that hot gas profile, etc. And that gas is going somewhere. I mean, this study won't tell you where it goes, but it tells you that there's a deficit of that mass on that high mass end of the halos. Now I show you where that goes. So this is a study that if we want to check where that goes, remember that first plot. It must enrich the filament and it must enrich the void, right? Otherwise, where it goes. So now I'm looking at the filament. Let's see whether we can see them in filament. So filament is it is one-dimensional structure. I mean, connecting the massive clusters. Here is massive clusters. Here is massive cluster. The filament is this one-dimensional structure by connecting them, right? And this is actually Jacob-Zeldovich back in the 1970s understood that why this highly filamentary distribution of dark matter exists. So he said the pancake would form collapsing from one dimension vertically, and then I later say when the pancake begin overlap, eventually it will forming this complex serial structure that compress gas layers that are surrounded by low density regions. So he discovered this while he was swimming in a swimming pool. In the pool, you can also see this. In the pool, that you can also see these caustic structures when the two dimension the water caustic they are merging together, you also see this. Right? Interesting. So when you do when you are having fun, you should also think about your scientific problem. Maybe you find something more inspirational than the pen and paper approach. All right. So then let's study these one-dimensional structures. So this is the Strong Digital Sky Survey, distribution of galaxies, covering a quarter of the sky, extended out to redshift 0.7. And for DESI, it will be even deeper. We are urgently waiting for the DESI first public data release. I hope it will be soon. I thought it's not yet been out, right, for the DESI year one. It should be even deeper for DESI. It should go to redshift 2, and of course for LSST, it will be possible also going to redshift 2 and possibly even higher. Now, this is blind stacking we did. So we believe the filaments are connecting the two halos. So we select a pair of the LRGs, the luminous galaxies. Notice here we're selecting a pair. We're not selecting single halos because we want to see somewhere in between of them. So here we select the central galaxies to have the stellar mass above some threshold, redshift in between this. This is low Z catalog of the SDSS. And people have also done that for the CMAX catalog as well and found similar results. But here I'm just showing what we do. So, and then we require those filaments to have a tangential distance in between this number and radius in between this number. So here, I mean, just imagine this is a filament, although this is not very strict, that we require the filament to be more perpendicular to my line of sight than vertical. If it's vertical, then after projection, I just get 1 point. Then I don't see any structures. If it's completely perpendicular, then I can see a decent filamentary projection on the sky. And that's why here the tangential distance is generally larger than the gradient distance. And this is and the detailed number is read from simulations that give us our indication. Anyway, in total, 260,000 pairs on the sky. And then we find those pairs. So here we find those pairs on the sky, and we cut them down. And of course, we want to uniform the size. We don't want to mess it up. We want to uniform size. So the big one we squeeze, for the small one we stretch, and eventually we stack them all together. We make sure the two halos on the two sides are completely on top of each other. And this is the map. Obviously, you see the two halo distribution. But that's not the story. The story is to see anything in between. Okay, how we do it. So that is the stack result on the left. And right-hand side is some control sample. Means we arbitrarily rotate the galaxies to an arbitrary angle, make the galaxy completely off-center, and then we should receive 0 signal. Right? Otherwise, I have a problem. So this is the sanity check. Arbitrary control sample. You see nothing here. That's reasonable. Okay, now we want to remove the halo contribution. Right? So here on the left, we did a little disk. Just make a disk and do a little bit average around each of the circular of the disk. Do this for the left, do this for the right, and subtract these two from here to see anything remain. And we do this also for the control sample as well. Here there should be no signal, otherwise I'm in trouble. Otherwise it means the data have a systematic, right? The question is whether left have anything. Let's see. There is. There is. After we do many tests, there is. This is how gas remain in between of the LRGs. Filamentary signal in between LRGs. And the right is nothing, of course. And for the control sample, you can do arbitrary number of times, because it's just arbitrary number of rotation of the angle on the sky. So you can build these statistics of the pseudo pairs on the sky. They are obviously centered at 0 with some little bits, indicating the noise level on your map. And the real detection is over here, which is 1.31 times 10 to the minus 8. And this quantifies the error of that, which is 0.25. In total, 5.3 signal detection of the hot gas in between of the pairs, which is either to do with the filament or to do with the very small halos that are basically not selected by the by the cut. And what does that mean? What does this detection? What does this Y value mean? So here is one equation, as I showed, the integration of the pressure profile along the left side. And electron density is equal to the mean electron density of the universe times 1 plus 2 delta, where delta is the density contrast, right? And remember, what is the mean electron density? It's about 2 or 3 electrons per cubic meter. It's very low. It's very low. Obviously, in the filaments or in the clusters, the density is much higher. So that delta is in the clusters, the delta is much higher. And then you can substitute this equation. This is the ionization fraction, helium abundance, and so on. You can substitute this into here. You get a joint constraint, a joint constraint. So delta of the density contrast times filament, times the temperature, times the RC is the radius of the cross section of the filament. Because here is a DL. Here's the equation along the left side, right? So there's a geometric function that you have to integrate over the cross section of that filament. So that is about 0.5 H inverse microsecond. So this term. Jointly, you get this times this equal to order of unity number, right? And so that means if your density contrast of filament is about 10, roughly about 10, then the temperature of the filament, hot gas, should be about 10 to 6 Kelvin. Right. So this is an observational evidence to show that the warm hot gas is there, and is with that temperature people previously seen from simulations. But this is a kind of a interesting study of that. So here, this is the fraction of the total baryon, and you can see for the filaments is really a large proportion. In fact, from the FRB study, we also have seen that. So the void for the halos is basically this value over here, and then also there's a component in void as well. So in the future, I think the LSST plus the CMB SAAO survey will be really powerful of localizing this, because it will have a much larger sky coverage and so on, and to do build a lot of statistics to do this kind of study. What time is now? Okay, still have time, and let's move on to even lower density region with the cosmic void. That is even higher. So here, I mean, that study is only possible with a large number of samples of the spectroscopic survey. I mean, I'm not sure photometric survey can do this, but we can try on that later. But that is only possible with a large sample of spectroscopic survey, which is from the simple size survey. So here, I mean, after the BR12, people have been, different groups have been trying to reconstruct the void distribution in the volume of SDSS. And there is this one void reconstruction, which gives you a large number of void with a mean redshift 0.32 and roughly the mean radius 13.6 H inverse microsecond. And so what we did is, I guess the battery runs off. And then we can stack them in ACT and Planck. Yeah, probably. We can stack them in ACT and Planck, and you see a little deficit of the void, of the signal in the center of the void. And then in total, it's about 7 to 9 sigma confidence level for ACT and for Planck, which is pretty well consistent with each other. And here we subtract the mean background contribution from the CKB unity, and then the central void is negative value because it's under that region. Now we can do a little modeling of knowing, just to get knowing of what these detection mean in terms of physical quantity. Here the model is very simple. The density of the electron is about MET bar times 1 plus delta. And here the delta is, we put it as a constant. In fact, we can do a better, we can do a better of this delta B, but this is a constant for now, and this is the temperature of that hot gas. Now we can put them back to the equation to fit the model to the quantity inside the void. You get a joint constraint like this, minus delta B. times temperature normalization is order of unit. Why minus delta V? Because in the center of the void, the density is lower than the mean density of the universe, right? So if NE is the number of density of void, that equals the mean density of the mean electron density of the universe times 1 plus delta V, right? So this NE has to be lower than NE bar. So delta V must be negative. Must be negative. And it cannot be more negative than -1, because otherwise this will be negative, and that's unphysical. So delta V must be, for void, must be a number between -1 and 0, isn't it? It must be lower than the mean density of the universe and must not be more negative than that. That's why we get a constraint like this. A minus delta V will become a positive number, and times temperature will be our unit. So that means the temperature of the warm hot gas inside the void is about 10 to the 6 level. Right. So yeah, so that is the drawing constraint we get. Okay. Let's see the. Okay, so this one. Hello. 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 Yes, a little bit better now. Hello. Yeah, and then we can also do some constraint on the neutral gas, because to complete that equation, we have also to search for the neutral gas, which is a small component, but also we want to see whether there's anything there. And what we did is we did intensity mapping correlation with the central galaxies of using both the Parkes data and also the Meerkat data. And for the neutral gas, is basically the H1, and that is the neutral hydrogen, which you observe from the 21 centimeter emission from the ground state of the neutral hydrogen. So here, the electron proton of the neutral hydrogen, they are in parallel, and here they're in anti-parallel. So radiation can come out of this neutral hydrogen if the energy state of that neutral hydrogen is transiting from this energy state to this energy state, and therefore the wavelength is about 21. And people have been have done this for many times for different data from GBT correlating with Deep2 survey, GBT correlating with WIGO-Z survey, Parkes cross 2DF, and Parkes cross WIGO-Z survey. And what we did is different from the previous Fourier study, but we do a more kind of a direct stacking of the LRGs on the map. And so here, these are the different maps from the Parkes survey. It's about 1,300 square degrees, and then we can stack the central galaxies and also the satellite galaxies on those H1 map. Right. I just want to fast forward to the result, and these are the central galaxy, satellite galaxy, and different modes of removal. And then you see a detection of all these different panels for both 10 mode and 20 mode foreground removals. And eventually we find a profile of the galaxies, central galaxies or satellite galaxies, and all above the Parkes beam at all different angles. Right? So you can directly see this effect when you're charting it. Right, and then you can do a little bit theoretical modeling of this. But at the moment, because the Parkes beam is really large, that it's really very hard to deduce very physical meaning result from this stacking. But I think the next step would be using the Meerkat better beam resolution map and to do the same stacking. Okay, and also we try to do the pair stacking as well for the H1. But the H1 in filament is very, very weak. And so here, basically, we do the same pair stacking for H1 and also do the halo fit and etc. But unfortunately, the residual shows no signal over there. But it can give upper limit on the omega H1 in the filament. So from the brightness temperature of these two modes, I don't use this anymore. And then you can deduce a upper limit of the H1 signal in the filament, and that is this number, and the column density of H1 inside the filament is very low. It's below 10 to 15 per square centimeter. Otherwise, we should already see it in the pair stacking. So Now I think it's time to conclude. Summary, most of the baryons are diffuse and warm-hot intergalactic medium with that temperature range. So that is a concept you can take home. And so in this study, we did a number of things. The thermal energy effect correlating with weak landing, and correlating with clusters, correlating with pair of LRGs. So the first one about lensing is a statistical study showing you the hot gas is much more diffuse around the gas clusters all the way out to the 5 times of the radius, etc. Exactly the same thing seen in the All-Strikers early simulation. For clusters, this one shows some of the deficit of the hot gas that in the halos and they are activated and being basically what do you call it, feedback out or like blow out from the center of the halos into the filaments and into void. So this one shows the deficit. And this one really showing you where they go. They are going to filaments, and we detected that hot gas in the filaments at 5 sigma confidence level. And really, this Y shows you the filament temperature is about 10 to the 6 to 10 to the 7 Kelvin, that kind of range. And here the void is the warm hot gas inside the void is basically measured at 7 to 9 sigma level. And then in the future, I think you have to kind of join constraint that hot gas in the void and also with some lensing or with some other galaxy study to separate the bias of the temperature and also the underlying density. And for these two, we are basically stacking the galaxies and pair of the galaxies on the intensity matrix, which is the neutral gas distribution. And you can see the cumulative halo 21 centimeter is detected at high level, 12 to 13 sigma confidence. And so this means 21 centimeter H1 can, intensity mapping can study the neutral phase of the hot gas in halos. But for the pairs, there's only an upper limit exists. So with more pairs and better sensitive map, then this might be measured at lower level for Meerkat or for the other radio surveys. So our results showing the missing baryon at low redshift is not missing, but related to the underlying loss of structure density field. And by using multivariate survey, we are approaching the true examination of the missing baryon problem. What I mean by true examination is that we are on the way to quantify this term and this term and this term and this term, and eventually check up whether that equals to 100% or not. Thank you so much. There's a question from the audience.
Yeah, okay, let's get one from the audience. Yeah.
Thank you very much. I think I'm completely convinced that that the distribution looks something like this, which is cool to see the observational evidence of that. I guess what I'm curious about is the baryons that you see in the filaments, which look like in excess of what you would expect just the baryons from falling to dark matter. Those are, as you pointed out, those would have been ejected from halos. Do we have any evidence about what masses of halos in particular those are ejected from? And in particular, what I'm thinking about is that really massive clusters have a deep gravitational potential, even if you set off a powerful AGN or something in the center of there. It's not completely obvious, at least to me, that you can provide either enough velocity or enough pressure to completely excavate it. The things may end up more sort of around the outside of the halo. But if you have a group scale, say 10 to the 13 solar mass halo or 10 to 12 and a half, then it's straightforward enough to actually blast things completely out. So when you're looking at the LRG pairs and you see this diffuse gas in between them, is it possible that that material is not really coming out of the most massive clusters, but instead is more likely to be ejected from the somewhat lower mass systems that still have hot halos in them, but have lower escape velocity?
Right. So that involves a comparison between the data and simulation.
Yeah.
So in this paper, we compare that with early simulation of Cosmo OWILS, overwhelming large simulation, and also the early illustrious, and we find a match. And in the recent work, so illustrious simulation have these two versions. So one is early illustrious simulation, the other one is TNG, which is a much later advanced version. The later one readjust the feedback strengths and reduce that because people think that the feedback may not be that large and they try to reduce that feedback and so on. But interestingly, our data match the early one. And also the recent work from ACT, from stacking the KIZ data and so on, also shows that the real data of the KIZ stacking from the LRGs in DESI on the ACT map match the early illustrates than the later one. They prefer a stronger feedback than the lower feedback. So that is something interesting, and we will looking into this in more details, etc. But unfortunately, because the signal noise ratio is low, so in cosmology, we always do this statistical study of a large amount. So we can only draw this conclusion in a statistical way. And then we're unable to look into each individual halos and so on to draw a conclusion.
Catherine, I think you can go ahead.
Oh, thanks. Sorry. Yeah. Hi. Thanks for the great talk. I think in 2018 there was a Nature paper by Nicastro, etc., who were looking at 07 absorption lines from distant quasars, and their conclusion is that the missing baryon problem is solved. What do you think of that?
Well, that's a good work, but I think for those observation lines, etc., and at that redshift, yes, you can conclude. But here we are more kind of directly into the hot gas that around the halos and etc. So I think this is what we're doing is a necessary step towards completing that equation or that question.
Yes, Ross.
Do you see? Maybe it's not possible to measure, but evolution. I'm wondering whether you need to actually extract the variance from the halos, or whether they might not have ever been here. What I mean?
Explain again.
Do you have to actually take out the hot halos, or is it possible that they never actually were in the space? Do you see this picture evolving with time to end up like this now?
Well, that's a good question. Yes. As the universe never been static. It's all has been driven by gravitational inflow and also the burst from the feedback and so on. Certainly at high redshift, that the scenario will be different. I think for now, for what we are doing is mostly on lower redshift. That mostly kind of not as low as other people think, but mostly below redshift 2. Certainly, if you want to quantify the hot baryons, like for instance in the EOR period, then almost all would be initially would be on the on the 21 centimeter intense mapping, and of course later on being whole red, fully reionized, and you probably measure that from the CMB quadruple polarization, quadruple anisotropy.
Maybe.
At what point in time is filament started forming?
The filament.
Yeah, filament structures forming. It may not have started like just after the decoupling of photons, which should have started.
Oh yeah, it has to start a much later time. What happened at universities after the decoupling time, the universe enter into dark ages. There's not much thing going on because gravity is not strong enough to form any stars and galaxies. So it's a pretty boring, less things happening period. But then once the first star and galaxy form, that's roughly about 1 billion years after the Big Bang. The potential is deep enough to pull into the hot baryon inside, and therefore to form the first star and galaxies. Those are very mature stars and galaxies, and they will emit a lot of ultraviolet radiation that it will gradually reionize the surrounding intergalactic medium, and they're providing this ionized bubble of the universe. And that's an EOR period, which a lot of low-frequency radio interferometer, including Hera on our land, is doing. So then after that, the first star will quickly die. They will only live in millions of years and so on. And then the second generation star will form, and they will form in more heavy metals and so on. And then during this process, the potential will further drive these baryons to form the galaxies, and the galaxy will basically coalesce and so on. And you will see these clusters being formed. And as they interact, the filament will also be formed as the gravitational inflow mechanism, right? So there will be a lot of filament in between of these clusters, and also the filament will also inject matter into the clusters. So this all happen below redshift 6. Yeah.
Okay.
Can I make a general statement? Like, can I see most of the matter is in filaments and voids? Can I say that universe has been inefficient at forming condensed structures from the start? Is it a wrong statement?
Yeah, no, when you say condensation, what do you mean? I mean, the condensation.
Because most of the matter is in filaments and voids, but it is not in the short condensed high density structure. Is it because the universe has been inefficient from start? Is it because of the fundamental law of entropy?
Yeah, so in terms of, it depends on what you look at, whether you look at the time or look at the redshift. If you look at the redshift, redshift from almost infinity to all the way to redshift 4 or 5, then the universe is really inefficient. That only at a later time the last structure form. But remember that the redshift and time is not linear dependent. The redshift below 5 or 6 is really a long time. The universe actually before that is actually a short time. So in that sense, the universe is efficient in terms of time. That universe spent much less time to do these, the hot plasma period, the thermal equilibrium, and also the decoupling and so on. But then use much longer time to basically form the galaxy and stars. And you would argue that is inefficient, yes, because gravity is weak. Simple. If you know that G number, the Newton's constant, right? The Martin Rees wrote this paper, just 6 numbers. If that G number, 6.67 times 10 to the minus 7, right? And which is, and then kilogram times meter cube divided by, meter cube divided by kilogram square, whatever, and etc. So that number, if you have more zeros, if it's 10 to the minus 7, 10 to the minus 9, 10 to the minus 10, the universe will be much bigger and much more interesting. The gravity will take much longer time to form the galaxies and stars, and our own galaxy will become bigger, and our own size will become bigger, and so on. And it will be more interesting because, and then the universe has enough time to form interesting structure and so on. And if you say the universe is inefficient, yes, the physical answer is gravity is weak, and to my understanding, is the weaker the better.
Can't I take it as like a thermodynamic system? Is there no chance I can associate it entropy? Because that's why it is inefficient, because
yeah, I have to think about a bit more. The entropy, most of the universe entropy goes into the black hole and so on. Will basically goes into this. So if you have less entropy, you have more entropy, then we can kind of eventually be all in the black hole and so on. The universe become much less interesting. But yeah, but okay, we can discuss that later. It's kind of a deviate from this talk.
Yeah, we're almost out of time. If there's any very short questions or comments. Okay. Okay, let's thank you. Thank you so much. The next one.